I'm going to do 3 example kinematics equations that you should have in your notes using each of the 3, and then I will make a separate video with a 4th example that uses a combination of the equations. So, first one, if a car slows down at a rate of 2.8 meters per second squared, how long will it take the car to come to a stop if it is traveling at 15 meters per second? First thing we want to do is draw our diagram, and I know my cars look like sombreros. The car's moving fast, and then it slows down and eventually comes to rest. Given and find. We know that the acceleration is 2.8 meters per second squared. This is why diagrams are important. I show in my diagram that the car is moving to the right. So it's moving in the positive direction and it's slowing down. Anything slowing down in the positive direction has a negative acceleration. So this acceleration is negative 2.8 meters per second squared. If you drew your diagram going in the opposite direction, your acceleration would be positive. So this is why I stress the importance of diagrams, that you draw the diagram and the directions match up. We also know that the initial velocity is 15 meters per second, and it comes to a stop, so the final velocity is 0 meters per second. And we want to find how long, so we're looking for time. Using the variables that I'm given, so acceleration, final, and initial velocity, and looking for time, the only equation that it would make perfect sense to use would be v final equals v initial plus at. V final is 0, so just rearranging to isolate t, we get negative v initial over a equals time. So negative 15 meters per second divided by negative 2.8 meters per second squared will give us the time. Time can't be negative, so it's good that we have 2 negatives that will cancel out to a positive. Dividing these gives us 5.357, keeps on going, seconds, equaling the time. And this is 2 sig figs, so time is approximately 5.4 seconds. Pretty simple, just use of the first equation. For our next example, a skier starts from rest and slides 9 meters down a slope in 3 seconds. In what time after starting will the skier acquire a speed of 24 meters per second? So here's our slope. Here's our skier starting from rest. And then the skier slides down the slope and will be moving. Given. We know that starting from rest, v initial has to be 0 meters per second. It tells us that the skier slides 9 meters. So that 9 meters will be my delta x, the displacement. And this is done in 3 seconds, so time is equal to 3 seconds. It also tells us that our final speed is 24 meters per second. What are we looking for? We are looking for time at the end. So in other words, how long the time is when v final is 24 meters per second. So one thing we know is that the skier is going to go 9 meters in 3 seconds down a slope. And the slope's not changing. In other words, it's the same hill, it's the same slant, it's the same angle. So whatever the acceleration is during those first 3 seconds will be the same the entire time. So the first thing we want to do is figure out what is the acceleration. We have a v initial, a delta x, a t. Just for the first part, we're going to look at these 3 things, and we're looking for acceleration. The only equation I have that has those 3 things is delta x equals 1/2 a t squared plus v initial t. My v initial is 0, so that goes away. Isolating the acceleration, we get 2 delta x over t squared equals a. So I just did the algebra from this step to this step. 2 times 9 meters divided by 3 seconds squared equals acceleration. 2 times 9 is 18. 18 divided by 9 is 2 meters per second squared for acceleration. Once I have acceleration, I can solve for my time when v final is 24 meters per second, using v final equals v initial plus at. I know v final, v initial was 0. I know acceleration. The only thing left now to find is time. So v final over the acceleration equals time, coming over here because I'm running out of room. 24 meters per second divided by 2 meters per second squared equals my time. 24 divided by 2 is an even 12 seconds. And this is 2 sig figs, so there's no rounding to do. My time to get to 24 meters per second is 12 seconds. Okay, and for our third example, an object starts from rest with a constant acceleration of 8 meters per second squared along a straight line. A, find the speed at the end of 5 seconds. B, find the distance traveled. C, find the average speed for the 5-second interval. So we'll start with our diagram. This is really simple. It's just any object. So I'm just going to draw a ball, starting from rest, and then going along a straight line and accelerating. What are we given? We know that since it's starting from rest, the initial is 0 meters per second. Tells us the acceleration is 8 meters per second squared. So it's speeding up in the positive direction. We know that the time is 5 seconds. And we want to find in part A, v final, in part B, delta x, and in part C, my average speed for the 5 seconds. So starting with part A, looking for v final, I've got v initial, a, and t. Use the simple equation, v final equals v initial plus at. V initial was 0. So v final equals my acceleration, 8 meters per second squared times the time, 5 seconds. 8 times 5 equals 40 meters per second. Only 1 sig fig, there's no rounding to do here. Going on to the next slide for part B. So in part B, we are looking for delta x. We have v final, acceleration, v initial, and time. It doesn't matter what equation we use. So let's use the second equation. Delta x equals 1/2 a t squared plus v initial t. V initial is 0. That cancels out. Delta x equals 1/2 times 8 meters per second squared times 5 seconds squared. Half of 8 is 4. 4 times 25 is 100 meters. So delta x, again, no rounding here. This is already 1 sig fig, equals 100 meters. This could have also been done using the no time equation, so I'm just going to do this off to the side using that equation as well. V final squared equals v initial squared plus 2a delta x. We should get the same answer. My v initial is 0. V final squared over 2a equals delta x. My v final was 40 meters. 40 meters squared is 1600 meters squared per second squared, divided by 2 times 8 meters per second squared equals delta x. 1600 divided by 16 equals 100 meters. So this is just an example of how it doesn't really matter what equation you use. They'll both give you the same exact thing as long as you have all the variables you need. And then let's look at part C, looking for the average speed. So your average speed is your distance traveled divided by the time. So our total distance was, distance traveled over the time. Direction doesn't matter here, so my distance and displacement are the same. So my average speed equals 100 meters divided by 5 seconds. 100 divided by 5 equals 20 meters per second. Again, this already has one sig fig, so no rounding is needed.